So I just double press this button?
That's it.
Oh, we are live. Wow, these are dope. Oh.
What's up, everybody? You're now going inside the mind of Kid Super. I'm gonna show you how the magic happens.
Hey, Meta, send a photo to Mom on WhatsApp. Cute!
Hey Meta, what mocktail pairs well with an avocado pesto pasta?
A refreshing cucumber lime mocktail pairs well with avocado pesto pasta.
Wow, that's fire.
All right, let's go.
Hey, Meta, call Eric.
Calling Eric.
Yo, what's up?
Yo, Eric, yeah, let's go with the silk.
Hey, Meta, what's the dinosaur with all the spikes down its back?
The dinosaur with all the spikes on its back is the Stegosaurus.
Ooh.
You look good.
Please welcome Meta Engineering Director Ulla Tørudbakken.
Okay. Hi everybody, and thanks for being here together with us today. Hopefully you enjoyed the little video that demoed our smart glasses together with our latest multimodal AI feature. I'm here to talk about infrastructure and the infrastructure that this runs on. So, infrastructure at Meta, our focus has always been open. In fact, that has been part of our DNA. We were a founding member of OCP. Last year, we contributed the Grand Teton 8-way GPU server that is a workhorse funneling most of our workloads in our data centers. And since over the past 12 years, we have provided more than 147 specifications into the community. Today, I'm going to talk about our path forward, building open rack-scale AI systems. And that's a journey that we would like to embark on together with you, the community. Before I talk about that, I'll talk a little bit about AI. So Meta is fundamentally about connectivity. Connecting, providing tools to connect the things you care the most about. Your family, your friends, your colleagues, and your business. Meta has been using AI for over a decade, both internal within our platform, but also as part of our tools. And last week, we released the latest AI assistant, Meta AI, that is now part of all our family of apps, WhatsApp, Instagram, Facebook, and so forth. What drives this is open source models. And we fundamentally believe that is the right way to do these things. It provides transparency. It provides safety. It enables security. And selfishly, may somebody say, it also provides a community effort to improve and enhance the models for better goods. And since we released Llama 2 last year, it has been picked up by a number of businesses and research centers and universities all over the world. So in my country, Norway, the public transportation service, as an example, Ruter, they are using Llama 3 fine-tuned on Norwegian language to analyze customer complaints. And last winter, in which there was lots of snow in Norway, that came to its use, to put it that way. So what has driven the innovations in AI for the past years, that is basically large language models. And large language models, they are based on a technology called transformers. And transformers has proven to be extremely scalable. Llama 2 that we trained last year, that was trained on 2 trillion text parameters. And we used a cluster of roughly 2,000 GPUs. This year, we just released Llama 3 that is still trained with text. It's a much larger model, and we have trained it with 15 trillion tokens. And we yet have to see where the diminishing returns start to hit us for this. So we are basically entering multimodality in which we combine text, audio, images, and videos to build models and services and tools that perhaps better would represent what we call what is the physical world. These models, they run on GPUs, and large number of GPUs. Back in a couple of years ago, we had 6,000 accelerated compute units in our fleet. Last year, we scaled that to 16,000. And by end of this year, we expect to have close to 600,000 accelerated compute units within our fleet. That's 100x growth over less than 2 years. From a cluster point of view, our clusters a couple of years ago, there were a couple of thousand nodes. Now our clusters is in the order of 20,000 plus. And this will continue to scale, and we expect at least a 10x increase in scale as we move on. And that is fundamentally funneled and driven by silicon innovation. So from 2014 to today, we have had a 300x increase in computational complexity and performance. And that will continue to scale through a combination of basically process shrink, going from 5 nanometer down to 3, 2, and 1.4. But fundamentally, silicon is also moving into more and more advanced packaging, from single reticles to multiple reticles on the same silicon interposer to wafer on wafer. And these large packages will be connected together in tightly coupled scale-up domains. And this also drives or impacts the rack scale system design. The Grand Teton systems we use today, we typically pack 2 of those into a rack. So that is 16 GPUs within a rack, roughly 15, 16 kilowatt. As we move to the next generation of systems, the power density will continue to increase. So we'll get into 50, 100, and several hundred kilowatt racks that demands liquid cooling. And this is, again, driven by higher TDP through advanced packaging, and again, tightly coupled scale-up domains. Also, if you look at this from a hardware point of view, the large clusters that we build, they will continue to be heterogeneous. Because when you build clusters like, in the order of 100K to perhaps even more than 1 million accelerated compute units, both from a supply chain point of view, but also from a model entropy and accuracy point of view, you benefit greatly from having diversity. So basically, we need to rethink how we do hardware. And we talked about this at the OCP in October. So I'm going to give you a little bit more details about what we think about. So basically, we need to get to commonality at the rack scale level. That implies a common rack, standard liquid cooling, and universal management. And what we think is the main building block here, that is the ORV3 rack. and that will have a set of accelerator banks. It will have a set of network or switch banks, and these are tightly connected together. It will have a rack manager, and it will have power shelves and liquid cooling manifolds. The accelerator banks are tightly connected to the switch shelves through a high-speed, cheap copper backplane. And the bandwidth can be adjusted to the number of lanes you actually use in the backplane and the number of switch trays you actually populate. Everything needs to be hot pluggable, so that implies, and that drives both serviceability. It also drives reusability. So it blind mates into a manifold where the water comes in, and the interconnect backplane and the bus bar. This also needs a close interaction between the data center. So basically, the liquid cooling and the power delivery, the facility water temperature, the blind mate quick connect, the manifolds, and also the flow rates that needs to be incorporated into the data center design. And at last, but perhaps most also equally important, hardware management that is CLUX. I personally like to think about this as the management of a traditional mainframe, where we have a number of throughs, compute unit, network units, power, liquid, that comes together and act as a single unit to deliver a single service. So what I'm getting to is that we fundamentally believe that the infrastructure for AI that needs to be open. It's based upon open software frameworks, it's open AI models, and also open hardware systems. And that model, that openness, that also works. We have PyTorch today, that is the most used framework for building AI models. That drives portability across platforms. Llama is another example. Open models provides better transparency, provides better security and safety, and avoid bias. And we, as a hardware community, we need to come together to drive this forward also at the hardware level. So to wrap it up, I think we need to pull this together. The rack comments that we talked about, the rack scale design, tightly coupled rack scale design, co-designed with the data center and the hardware management. And as George talked about earlier this morning, we are kicking off an open AI systems initiative to drive this forward. So with this, I would like to leave it off for a person like me that has been building supercomputers for many years. A dream that would be to an interactive supercomputer which is open and it's as easy to operate and debug as a bento notebook. And we hope that we can make this happen together with all of you. So with that, thank you all. Have a great continued day here at the OCP, and thank you.